All right, I would suggest before we do the recap, let's now revisit the semester calendar very quickly. So because we got one more test and one more assignment for you. So let's take a look. That's the updated one, right? Since we announced a little bit earlier, shortly after the reading week. Well, actually earlier. Okay. So we are now here, 10th of November. So we are here. So on schedule, I can definitely release assignment number 2. I'm just finalizing the detail. I'm basically done with setting up the assignment. I think I should be able to release that a little bit earlier, maybe tomorrow early. I can even try tonight. I just need to finalize certain details. But if I can release that earlier, I'll release that earlier by the same deadline. So you just get a little bit more time to really take a look at the assignments and then try to struggle through certain points. There will be some theory part and also some programming part like last time. I think the programming part will be interesting for you to solve this time. It's kind of interesting. But anyway, you will see that when you see that either tomorrow or Wednesday. Tomorrow latest, I should say. And the assignment will be, excuse me, it will be due next Wednesday, the 19th. And then I think we can try something like last time. I will confirm with you. So on the 19th class, we can possibly cover a little bit more of new stuff, and then we can dedicate maybe at least 30 minutes, 40 minutes to do some review. You can ask questions about the slides like last time. And then on the tutorial session on the 21st, next Friday, we can, again, go over the programming solution, maybe go over, there will be one proof for you as well this time. Okay, it's going to be interesting proof too, definitely for you to think about, and I can go over the insights as well once the solution is posted. And your test number 2 will be on Monday, November 24th. Please notice that this is postponed for 1 week compared with the originally scheduled one, right? That's something we already announced way earlier. Okay, so that's going to be your test. I will also post a PDF guide like last time, but I can expect the format will be pretty much the same. There will be programming, there will also be written on the e-class as well. Okay, format will be the same. And then also our exam will be in December. I'll also reach out to you to schedule some like a review session as well. I think we can do at least 2, just 2, depending on your availability. We'll see. Okay, let me see anything else to talk about. All right, so if you want to talk about your test number 1 result or get any feedback, reach out to me, office hour as usual. Okay, Monday, Wednesday, 6 p.m. Okay, in person. And then, yeah, so that's something, just please pay attention to the deadlines. Any questions? So today, we're going to do a quick recap, careful recap just about the Dijkstra algorithm and also the critical terms that we kind of introduced for the weighted graph. Let's revisit them very quickly as a recap, and then we'll do a very detailed tracing for some example. We'll do a slightly more complicated one than the one we talked about last Wednesday, and then I will give you some more complicated one in the assignment for you to try. Okay? And then, of course, in the actual test, you might be given something similar. Okay. Let's do a recap. Oh, one thing I forgot to mention as well. Let me just do it quickly. So last Friday, for the Zoom tutorial, it's really exceptional. I think normally I definitely prefer in person. Okay. But anyway, so if you look at the lecture site over here, you will see that under tutorials, week number 9, right? So you got the notes over here and the recording, right? It's there. And last Friday, I basically just finished off the breadth search exercise that we did earlier in the lecture, and just to finish that off, right? Just make sure you can do the complete thing as well for yourself. You may have to combine what we did on the Monday's lecture, I believe, and then also on the Friday tutorial, combine them together, right? That's a complete example. And if you look at that for the breadth search, I'll give you another exercise to try from the assignments, right? You can definitely get used to how to trace, right? So that will be kind of the thing that you want to feel comfortable about. So just one moment. Especially for the breadth search, you really want to pay attention to about levels because we divide the vertices into levels. Level 0 by default is going to consist of just the start vertex. Question? In Q list. Let me double check after class. Yeah, remind me again. So I'll double check. Could be possible. Yeah, please let me know after class. Thank you. Yeah, just in case I got any mistake, please do let me know. I'll fix it. Okay. All right, that's good. Okay, let's now move back to last Wednesday. So last Wednesday, we clarified this important idea about the difference between back edge and cross edge. So just remember, cross edge does not necessarily imply you will have a cycle in the case of the directed graph. Just remember that. Okay? And also you can go over the example just to verify. And then we spoke about this adjacency list and also adjacency list implementation strategy. So about the classes and also right here. So unfortunately, well, I wouldn't say unfortunately, so I decided that for your assignment number 2, we are actually going to still stick to the edge list strategy since you already built some familiarity from assignment number 1. And instead, I'm gonna let you try to really build up on the existing either Bradford search or Depth search, either one of them, depending on which one I'll give to you, and then use them to answer some graph questions. So I think that'll be some interesting exercise for you to try. Okay, so you will see that when you get the assignment. But I will still cover the final implementation strategy, which is called adjacency matrix. That one there is going to use a 2D array. And what should you study for the exam for the strategy? So you will also see the slides. I can just point to you. It's already there. So if you look at the slides right here, the final one for now will be slide number 70 and 71. So these two slides really summarize about the ingredients for implementing, the graph using different strategy. And also slide 71 is about comparing the runtime complexity, okay, of different strategy. Of course, you don't want to memorize them, right? I'll provide them to you, and then when we get there, possibly Wednesday, or maybe early next Monday, I'm going to go over the table together with you, especially some key entries that are highlighted. You want to really use this table here as a guidance about understanding the 3 different implementation strategies. I might ask you more like a synthesized kind of question in the exam to really compare these 3. So I'm giving you a hint. Definitely, you want to take this as a study guide for understanding about the runtime. But we'll go over that certain entries. But before that, it doesn't hurt to really go ahead and just study for that. And at least your test number 2 is going to cover up to here. At least, okay? If I can cover some new material, we'll do that. Oh, by the way, also like last time, right? I also want to clarify, just for those of you who are here, I will confirm maybe later on the E-class as well. So if you look at the calendar here, okay? So your test will be on the 24th, right? So today we're gonna cover stuff, and also on Wednesday for sure, and also these 3. For sure, these 3 classes on the 17th for sure. I might cover some partially, maybe some new stuff as well on the 19th. So all those will be covered in your test number 2, right? So for sure, just want to let you know, okay? But whatever, nothing new in the tutorial. We just go over solutions and do some review. All right, and slide number 70 and 71. That's for your information. Okay, okay, let me just go back to the Dijkstra. And then we'll start from there once we have done with the recap. One moment. There we go. Okay. Okay, back here. So that's a visualization for the adjacency list. So especially you want to notice the new thing we have added is for each vertex over here, you have an extra list that's going to point to all the incident edges for that particular vertex. So this is actually going to make some change to the running time when you think about it, right? So that's something you have to get into as well. Okay, and then we started with the concept about shortest path and also weighted graph. So these are the terms we have to use when we trace the Dijkstra algorithm today. So let's revisit them very quickly, okay? So we talk about individual weights on the edges. So we got, for example, some numerical value, and there is a fundamental assumption about the shortest path that we consider for Dijkstra, which is the every weight should be non-negative. Okay, I think I wrote this somewhere. Yeah, non-negative. I will focus a little bit more on this non-negative assumption a little bit later once we understand the Dijkstra algorithm very well. And then we'll see what if you relax this assumption here. What kind of error can it cause? Right? That's something we'll see later. But just remember, it's a very important assumption. And whenever you want to justify the correctness of the Dijkstra's algorithm, you will actually have to use this assumption as a basis for justifying. Okay? You will see in the assignments. All right, so we talk about the weights, which we just use W. That'll be the weights between any two vertices because, for example, the weights between this and this will be 802. And then we talk about the length and also weights of a particular path. Basically, let's say here, there is one path right here between this and this. What will be the length or weights? Just add up the weights together, right? It's going to be another number, basically using the sigma notation, right? That's something we derived last time. And pay attention to this particular function here. It's lowercase d. Whenever you say lowercase d, you pass source and destination. So here, when I say the little d of u and v, what does that mean? That means I want to return the minimum weight sum between these two, u and v, provided that they're connected. If u and v are not connected, the so-called distance or shortest path between them will just be infinity, plus infinity. If there's any shortest path between them, you have to return the minimum summation of the weights between u and v. That's something that Dijkstra is going to calculate for you, which you will see today. Okay? Also, I'm going to write it down a little bit later. So little d here is what we call the true shortest path. So the true over here means a lot. All right, so true here. That means the ultimate answer you want to get into about the shortest path. There might be some intermediate values you want to calculate, but along the way, you should really get to the true value at some point. All right, so that's about the terms you should know, especially the little d over here. And then that's the Dijkstra algorithm. I kind of put it in the more like a bullet point. I'll try to see if I can also show you when we talk about runtime, maybe on Wednesday or early Monday next week. So I'm going to maybe give you another flavor about the look for the algorithm, more like a pseudocode-like, but you can definitely translate it into Java if you have to. Let's now just, without reading off, but let me just remind you very quickly. So there are two things that we have to maintain throughout the course of the algorithm. One is, notice that it's a capital D, not lower d. You would hope that the capital D at the end of the algorithm is executed, capital D should really match the lower d. Okay, we'll see that. Okay, and also we got the little a here standing for ancestor. So these are the two things we have to update whenever applicable in every iteration. So the Dijkstra algorithm is an iterative algorithm. So we have to keep updating these two variables. And then for each, and then it's more like a nested loop. So we're going to make sure the priority queue we have, we're going to keep extracting the minimum d value from there. And then we're going to, for every vertex we can extract, we're going to consider its adjacent vertices. We're going to keep doing it. And then every time we'll check this particular equation and make sure if we can find anything that's smaller than the minimum, we're going to update. It's pretty much like if you have an array of integers, how can you find the minimum? You keep some minimum so far variable, and then as soon as you find anything that's smaller than the minimum so far, update it as the current minimum so far. That's basically the idea, we'll see. Okay? And this is a very important condition as well. Okay? Whenever we are actually looking at the adjacent vertices of a particular vertex, we make sure we only consider the neighbor that is still in the queue. If the neighbor is not in the queue, we skip it. Okay? Well, when we talk about the runtime later for the Dijkstra algorithm, you'll notice that this particular Boolean condition here, that we only bother to check this equation when we actually got this particular one satisfied. It's going to make a big difference in the runtime. Okay, we'll see that. Just give you a heads up. Okay. All right, and then at the end, we're going to get some result. Well, we'll see. We're going to use one example to illustrate everything. Any questions about the basic? Any turn, anything conceptually not clear? Let's trace it. All right. Okay, that's the example we did last time, but that one is not very exciting. That one you can see, we actually don't really have any connection between x, y, and z. Not very interesting. Let's now make the graph, still the same number of vertices, but let's make it more complicated. So we do have something to talk about. Okay, let's start with this. Okay. Before that, let's write down something. Imagine that we're now more like Oracle. We look at this graph over here. Before we even try to run the Dijkstra algorithm, let's set up some standard or evaluation criteria to make sure Dijkstra can really calculate the right result at the end. So what I want you to do is, remember the little d that we talked about, that's the true shortest path. I'm going to write it down here. Now let's consider, let's calculate just manually. What is the true distance between W and W? What is the true distance between W and X? So let's say we want to start with this. Let's say this will be something like a start vertex or like a source vertex. We want to see what's the shortest path from every other path. Sorry, what is the shortest path from every other vertex into W? Shortest path, okay? And then what is the little d from W to Y? What is shortest value from W to Z? Okay, let's work out this one first. That's the ultimate answer we will expect Dijkstra's algorithm to calculate for us. But let's understand what they should be first of all. I'll start you with W to W itself, the shortest path is, takes no edge, takes no weights, 0 by default. That one's easy. Okay, what about from W to X? 40? 30, right? How many edges would it take? 3 edges. So number of edges do not necessarily mean it's actually more costly, right? It really depends on the weights, the sum of the weights. Turns out, you should really go, if you go directly here, it's going to be 40. But if you go here, 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 20, 25, 30. That's the minimum, all right? 30. And what about WY? 25, right? Also go that detour, basically, this way here, right? 25, and then for Z, 20. Thank you. Again, the reason that we are doing this is because I want to show to you there will be certain evaluation criteria for Dijkstra algorithm, which is something called looping variance. We might get there today or maybe on Wednesday. To really see that, first of all, let's now see what should be the ultimate answer Dijkstra algorithm should really compute for this particular small example. And then I'll show you along the way, you will see how the Dijkstra algorithm is going to gradually approximate into this answer in the iteration. Okay, let's keep that in mind, all right? And notice a little d, not a capital D. Okay, I'll make it a little bit smaller. And then let's now do the initialization, okay? Okay. So initialization, let's now initialization. Let's use a table just to show to you. So we have different value here. We got D value, and also we got an A value, ancestor, D and A. All right, so let's get all the vertices in. We got W, X, Y, and Z. W, X, also Y, and also Z. Right? So these are all the vertices. For each one of them, we should really make sure we always keep track about 2 variables, the capital D and also lower a. Again, capital D, very different from the little d. Eventually, the capital D should really get to lower d at some point. We'll see exactly when. All right, so in the beginning, to initialize, we'll simply get the capital D value only for W, the source. So we call W the source. That's why Dijkstra's shortest path algorithm is also called single source algorithm. You got to determine which source you want to start from. Single source. All right? So we got 0 here, and everything else is going to be plus infinity. So this can guarantee for the very first iteration, you're going to choose the source, guaranteed, right? Just the setup. And for the ancestor, we're just going to put nil, which means undefined, okay? Ancestor, 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 and ancestor. That's an initialization. All right, let's now also annotate a graph just to show this, right? Because we're going to update these values as well later. Okay, let me just put it here. So we got d of w, 0. A of w is nil. And then d of x equals plus infinity. And also a of x will be, you know what? Let me write a little bit to the left. I think that'll be better. So d of x will be plus infinity. A of x will be nil. Similarly, d of y plus infinity. A of y, nil. D of z plus infinity. And then a of z, nil. And we also have a priority queue. Let's write it down as well. So we have a priority queue right here. That should be good enough. And if you look at the initialization step, let me just remind you very quickly. So on slide number 53, so that's the setup we have just done, right? 0 and nil. Also, we're going to put all the vertices into the priority queue. It doesn't matter the order in which we put the vertices into the queue. Because it's a priority queue, it's not first in, first out. It's going to be determined by the d value. Okay. So I'm going to actually put all the vertices in. So I got w, x, y, and z. Okay? So this is the priority queue. Okay? Let me put a star here. So this is a minimum key priority queue. Minimum key, and the key is about the d value. Every time you want to extract some vertex from the priority queue, you want to extract the one with the minimum d value. If there are two vertices with the same d value that's minimum, you can extract either one of them. That's okay. Okay, minimum key. Okay. Okay, so that's about the setup. Let's just make sure everything is set up, and then we can now start the iteration. Right here. Minimum key. Right here. Let's now put a trace table. Because it's iterative, so it's better to really lay out exactly the iterations. And then there's something called looping variance, which I will give you some simple example. We don't have to jump directly to the looping variant for Dijkstra, but I'll give you some highlights or remark so they can prepare us for Wednesday. Okay? So let's draw the table. Okay? It's going to be a big one, so I will try to save my space for that. So let's say here we got different columns. Column number 1 is going to be the iteration. Iteration number, starting from 1. You can think about the initialization we did, it's like an iteration 0, but let's not go that way. Just go iteration number 1, 2, 3, 4, and so on. And then the minimum d value should be extracted. We're going to keep track of that as well. And then for each iteration, what kind of changes do we have to make? Let's make it clear here as well. Okay, I think that's good enough. I think for your assignments, I'm also going to ask like a table to be presented. I would say just try your best, to kind of mimic the structure here. I might ask you any questions related to the table or anything I kind of annotate here, right? Just make sure if you got any confusion, any doubts, stop me anytime. Iteration number 1, okay? Let's now take a look at right here, according to the algorithm. So while the queue is not empty, we're going to stop the Dijkstra as soon as the queue is empty. Right now, it contains all the vertices. We just started. And then we're going to find out the vertex with the minimum D value. So once we find it out, we're going to reach out to all the incident edges. Okay? And for all the incident edges, we got to make sure we only check this equation here if the other end for the incident edge has not been visited, which means it's still in the queue. Well, that's something we're going to keep doing. Okay, I just want to remind you the text. Okay, let's see. So iteration number 1. 1 here. Okay, so now which vertex should we choose? W. It's by design, always. Okay, for the very first iteration. So W is going to be chosen. So W over here, where D of W is simply equal to 0. Okay? And then, it's blue, right? Okay, well, why don't we say, now this guy here has been chosen, right here. And given that 1, 2, and 3, all the neighbors are still in the queue. X is in the queue. Y is in the queue. Z is also in the queue. So we're going to do that equation check. We're going to do that relational check. So I'm going to use this to reach out to every one of them. Reach out to this, reach out to that, and also reach out to that. All right? And then for every one of them, we have to, actually I can say something here. You can think about X, all the vertices, X, Y, and Z. X, Y, and Z. All they are in Q. So that means we have to consider all of them. Okay? Let's say, for example, at the moment, the D value here is infinity for X. So that means so far all we know is the shortest distance from W to X is known to be infinity. As long as we can find out in the current iteration something that's cheaper or like a shorter, we should update the infinity to something else. Do we have one? Yes, we do. Because if we go from W to X, in that way, the weight should be just 40. 40 is strictly less than infinity. So we should update it. All right? It's very important. Okay? So what we do is we say, I'll write down the exact check. 0 is this number here, plus 40 strictly less than infinity. That means we should update it. So that means we should really update D of X to be 40. And one thing, let us check from the oracle. Okay, let's go above this algorithm. You can see the capital D for X is 40. The lower D for X is 30. That means we are not done just yet, just the temporary value. Right? It's very important. I want to put it down. Okay? At this point, we know that this is not yet equal to the little d. Okay, really notice about this annotation I'm putting. That's going to help us understand about the looping variant later. All right? So I just handle this edge. How about this one here? Similar, right? So 0 plus 30 strictly less than infinity. So we should update it as well. Okay? Oh, by the way, when I update this one here, that means now the ancestor for X in the shortest path should, rather than undefined, it should be W. Which means somehow when I actually calculate the shortest path, it should be W followed by X. We'll see exactly. Okay? So this one here should also be updated to capital W. Okay? I'm going to run out of space very soon. I will also put something here. The little a of x is equal to w. Okay, I'm going to put both sides. So two things will update. One thing and second thing, right? These are the two. Okay. All right, about the second one, right here. So we know that 0 plus 30, right here, strictly less than infinity. That means we should update it. So d of capital Y is now 30. And if you compare that, d of Y and d of Y here, 25, not yet there. All right. Also, not equal to d of W and Y. And at the same time, we should also update right here, a of Y should also be W. All right. A final incident edge to handle this one here. Okay. So here we're going to do 0 plus 20, which is this way here, less than infinity. That means d of z will be 20. This one is interesting, right? You can see now d of z is already 20. It has reached there. However, as far as the algorithm is concerned, it's not finalized just yet. All right? I'll put it down. This one here happened to be just the same as d of wz. Happened to be. However, it's not final yet. Not final in the sense that the vertex z is still in the queue. So that means at some point it will still be chosen. So we still may have a chance to update it. But in this case, we know that it's not possible. Right? Okay, so this one here, let me highlight it specifically. Reach there, but not final yet. All right? And that one there, we should also update the AW, the A value, A of Z, W. Okay, so this part here should be 30, and this one here should be W. And this part here should be 20, and that should be W. Okay, as soon as all the incident edges have been handled, you can remove this particular node. And then we can remove W from the queue. All right, so now as soon as we remove a vertex from the queue, that means whatever capital D value there is finalized. So this one here, that means the capital D of W, in this case, is simply 0. It's matching the 0. That's true, right? The true distance is equal to D of W to W. And this one here is final. Okay, I'll use orange there. All right, so we're going to remove W from the queue. And then we're done with the first iteration. The later iteration will be very similar. Remove W, and then there's the first one being removed from the queue. Okay. All right, any questions about the first iteration so far? Okay, question?
Does the iteration only end after you've removed that node from the queue?
Yeah, you can think about removing that vertex from the queue is the last step for the iteration. You can think about it. It's a very important step over there. As soon as the vertex is removed, that's about the point we can evaluate the looping variance. But we'll see. We can talk about looping variance. Yeah. All right. Okay. Now, second iteration. Okay. We're going to follow something very similar, except we haven't really reached the case where some neighbors may have been removed from the queue, in which case we don't consider them. Okay, not yet, but we'll see. Okay, let me just move a little bit. All right, so now let's do iteration number 2. Let me use, how about orange? Okay, question. Which one should we pick? Should we pick X because that follows W? Z, okay. Choose the one that's the minimum, right, for the D value, okay? So we're going to pick Z because the D of Z right now is 20, which is the minimum. All right, and then you can see that Z over here has incident edges that will connect to here and here. However, remember that important condition right here. We only consider this equation here if the neighbor is still in the queue. If they're not in the queue, we don't even consider that. All right, that's important. I'll write it down. So here, the neighbor W is not in the queue. They are not considered. It will turn out this is very efficient. Turns out it will be the efficiency that we can save, the time complexity. So we only consider only one edge, which would be right here. Okay? So we have picked Z right here. And then we only have to go this way. All right? Now, I will pause for a bit. This is very critical here. Now, exactly what kind of inequality I'm going to check? Tell me the number. What plus what? Less than what am I checking? When I want to reach out to Y. Y should be checked because Y is still in the queue, right? What exactly would be the number I have to check?
Plus 5 less than infinity?
30. Not we don't have infinity anymore, do we?
30,
Yeah.
Distance of Z plus the edge number, so 20 plus 5.
Yep. Yeah, you guys got it, right? So I think you should remember infinity has been wiped out already, right? In the previous iteration, yeah. After the first iteration, all the things reachable from the initial vertex should not have infinity anymore, right? Okay, good. So you guys got it? So let's now put it down. So it's gonna be this 20 plus 5 less than 30. So 20 plus 5 less than 30. So we should do the updates. 25 less than 30. So now what we should do is we should really say D of Y should be updated to 25. At the same time, we should also update the ancestor. All right? So now the ancestor of Y should be equal to the Z that we are talking about. That means in order for you to really reach the shortest path, you got to go through Z. All right? So I should really update this one here to be 25. This one here should be Z. Think about what's happening here. Before, when I have ancestor right here, that means the shortest path so far is to go from W to Y. But now I find a better one. It's going to go from W to Z and then to Y, in which case Z is the ancestor for Y, for the shortest path. All right? Z. All right, nothing else. Okay, so after this, just before I do anything further, so also let's take a look at this value here. This value here, you can see 25 is the same as 25 right here. Happen to be the same. But we're not final yet because Y has not been removed from the queue. So let's now try to annotate it. So this one is exactly equal to D of W to Y. However, it's not final yet because we haven't really removed it just yet, not yet. Okay, so exactly equal to it, but not final. All right, so now we have considered Z completely. So now we can remove it. So now we can remove Z from the queue. Oh, actually, I should really use orange to be consistent. So we can now remove Z from the Q. And this one tells us that as soon as Z is removed, so this will be the second one. Now, whatever the Z value is right here, like a 20, is considered final. It cannot be changed. No way. All right. So this one here, so we have D of Z exactly equal to D of W and Z. And this one here is final. All right. Okay, like that. Right here. And then, okay, so this will be the end of the second iteration. Okay, we got 2 more iterations to go, and also to show you how exactly to use the ancestor, and then I'll make some remark. But I think I'm just about halfway. So otherwise, I don't want to drag another 20 minutes without a break. Why don't we pause over here, take a short break, and then we'll continue. Okay. You can get your iClicker ready, and then we'll do that quick. All right, let's now continue. As you can see, the way we kind of run the iterations, every iteration at the end, we're going to remove the particular vertex we have chosen from the priority cube. And that particular vertex has the minimum capital D value. And then we know that initially we put all the vertices into the priority queue. And the algorithm is going to terminate when the queue is empty. That tells us exactly how many iterations that will be for this Dijkstra algorithm. How many? Josh, tell me. How many iterations in total? I don't know. Okay, it's okay. Yeah. Anybody? Go ahead. 4. Can you make it more general?
Yeah, I didn't know generally. For this one.
Oh, this one 4. Yeah, generally. Yeah. Yeah, exactly. Okay, that's good. Yeah. Okay, so that's something we can summarize a bit later. I just want to mention that. It just came to my mind. Okay. So the number of iterations that you're going to see will be corresponding to the size of the vertex set. Okay. Right here. Okay, let's write it down. So here, eventually, we're going to see the number of iterations. Okay. The number of iterations exactly equal to the size of the vertex set. Right? Always, just the way it's set up. Because we remove one vertex at a time at the end of each iteration. All right, let's now continue. Next iteration. So now we got only 2 vertices in the priority queue. So we know that we got 2 more iterations to go. Now, between x and y, what should we choose? X, agree? Because, oh, sorry, y, beg your pardon. Because you look at that, so now we got 40 for x. We got 25 for y. Choose a minimum. Of course, choose the one, that's y. Right? All right, so let's pick that. And then I'm going to say pink. Okay? Right here. Okay, pick that one there. And then iteration number 3. And that one there, we're going to pick vertex y. And then the d of y is equal to 25 right here. All right? And then you can see that we got 2 incident edges right here. But this one here will connect to a vertex that does not exist in the queue anymore. It's been removed. So we don't consider that. All right? So here we got W is not in the queue. It's not considered. Of course, we got to consider this one here. You want to try again? This time. What should be the equation that we'll check this time? You. This time. What exactly should we check?
25 plus 5 compared to 40.
Exactly. Right? Good. Awesome. Okay. Yeah, exactly. So I think it's just a matter of practice, really. Once you redo this one, I would suggest before maybe tomorrow I release the assignments and also do that complicated one in the assignment. I think you get a very good grasp about how the Dijkstra work. And then later on we'll talk about loop invariance later. All right, so for this one here, we're going to do 25, which is right here, plus 5 less than 40. So 25 plus 5 less than 40. Apparently, that's true. So we're actually going to say d of x should be set to 30. At the same time, the ancestor for x should be set to y rather than w. Okay? Yeah, when you do the exercise, if you can actually able to do it, maybe putting them in different colors for different iteration, that can also even tell you exactly the evolution for the values. We're basically approximating, gradually progressing towards the final true little d value. All right, so after this, we're going to remove the y from the q. But before that, I can also say something like here. D of x right now is 30, which is the same as this 30 here, but not yet final because x is still in the q. So this is also equal to d of w to x. However, it's not yet final. Not yet. This one here, not final. And then I'm going to remove the y from the q. Remove y from the q. As soon as I remove y from the q, it doesn't exist anymore. Then I can say it's final. So this will be number 3, right? So number 3 being removed from the q. And then, so here we say that d of y is exactly equal to the true distance between w and y. And this one here is final result. All right, that's a third iteration. Let's now do the final iteration because the queue is not empty yet, not just yet. We got one more vertex, right? So for that one there, let's now do a final row. But that one there should be rather easy to update. Okay, so what we get is, let's say, so apparently we're going to choose, that's the minimum, right? That's the only one left, which is 30. So that one there, we're going to choose it right here. Oh, sorry. Right, choose it right here. Okay, make it smaller, right here. And then here I'm going to say, I'm going to choose x because the d of x is equal to 30. Okay, sorry, it's a little bit down over there. And here you can see for the incident edges. Oh, by the way, this one should be pink. I forgot to annotate it from the previous one. Okay. So here for x, you basically got 2 incident edges. But the thing is, w and y, they have both been removed from the queue. So we don't consider them. No calculation will be needed. So in some way, this iteration here is very quick. Okay. So now we can say that over here, w is not in the queue, and y is not in the queue. They are not considered at all. Not considered. Okay, there's one more step. I will put a star star. Okay, I'm going to put it here. Okay, star star. The last final step for the 4th iteration is going to be, we're going to remove x from q. Remove x from q. And as soon as we do that, we know that that result should be final. So now we see that capital D of x, capital D of x should be equal to the lower d of w and x, which is 30. You can see 30 here and also 30 here, right? They match. So we're going to remove x right here. So now Q has become empty. So 4 iterations. Now priority queue is empty. So now let's examine. The Dijkstra algorithm now terminates after 4 iterations. Now, according to what we said in the slides, I'll also get back there, and let's examine the 2 results. Okay, first of all, you can see the capital D is exactly equal to the lower d, right? That's something we actually have been annotating along the way. So that one there, you should have no trouble, right? We are really getting that. So here we are saying that the shortest path from W to W should be weight 0. The shortest path from W to X should be of weight 30 and 25 and also 20 for the other 2 vertices. So the capital D value is now finalized. Let's look at the ancestor. That's the interesting bit. Okay? Now and then I'll help you a little bit here. That could be a little bit confusing. Let me just copy this one here. Let's put the final result again. So let's say upon termination, of Dijkstra's algorithm, let's now just copy just the ancestor value just for now, okay? That's something we want to focus on. So AW here doesn't change, it's nil. A of W is simply just nil. A of X is Y. A of X is Y. A of Y is Z. A of Y is Z. And finally, A of Z is W. A of Z is W. Okay, let's build, again, another 2 tables, just to be 100% precise, okay? Table number 1. Let's figure out the ancestor path. So we're just going to get the different destination. So we got X, we got Y, we got Z. Normally, we don't really have to list the path for W, because W to itself is already the shortest path. That's why I just put it nil, like empty in some way. Okay? And then we're going to put ancestor path first. And to work this out, you just got to look up, right? Exactly. So now, for example, you can see that over here. Let's start with X. First of all, you start with the X itself. And then you see that, okay, let me use a different color. Let's say I want to work out for X. You start with X itself. The ancestor is Y. You go to Y, the ancestor is Z. You go to Z, the ancestor is W. You go to W, here it's nil. It's as if it's empty, so you don't need to copy that down. That's the ancestor path, which goes like X, Y, Z, and W. Right? That's the ancestor path. So be careful, in the test or exam, if I ask you about ancestor path versus shortest path, they're different. Well, they're reverse of each other. Right? All right, let's now do a practice pretty quickly. What about the ancestor path for Y? Exactly. ZW, you're missing Y itself. Just remember the node itself should really is considered as ancestor because you eventually got to reach there, right? Good. So it's going to be, so if you start with Y here, and then first of all, you go to Z. And you go to Z, you go to W. And that's it. I can try to align that a little bit better. Okay, you can see what I'm doing here. Okay, finally, let's now for completeness. What about the ancestor path for Z? So we start with Z here. The A of Z should be W. So put Z itself first. And then its ancestor is W. And W itself got nil, so we don't, that's really the starting point for tracing the ancestor. All right, and then you will see that on the slides, we said you should really consider the reverse of the ancestor path. That one there magically is going to give you the shortest path. All right, let's now do that. So what we do is, let's now try this. We still got the same list of destination. So we got X, Y, and Z. And here we got shortest path. From the source, W. Remember, W was the initial one that we start with. Be careful, right? So whenever you want to perform the Dijkstra algorithm, you want to think about what shortest path do I want to start it from? That should be the starting point. Okay? You will see that notion also in the assignments, right? Just be clear. Otherwise, if you start with, for example, Y, it's not going to give you the shortest path somehow, in the right, not necessarily for the right path that you want. Okay, and then this one here, let's just get the reverse. The reverse of this is going to be W, Z, Y, X. That means I'm actually going to get W, Z, Y, X. This is the shortest path in terms of the weight sum from W to Y, or W to X, beg pardon. All right? It's actually very nice, actually, because when you are actually updating the algorithm, you don't really update like a sequence. You only update a single node as the ancestor. That's something you want to get more used to, okay? Well, but I'm tracing that for you, so hopefully you can see at least how it is supposed to work. All right, fine. And for this one here, the reverse is going to be W, Z, and Y. And this one here is going to be W and Z, okay? So these are the ancestor path, and these are the shortest path. They are reverse of each other. All right, that's a complete tracing. Okay, guys, any questions? So for the assignments, I'm going to give you something more complicated to actually keep track. So you really want to practice about how to compute the shortest path. So you definitely want to make sure you know about the initialization over here. And also, you may just want to, just for your kind of best learning, figure out yourself what's going to be the little d value that eventually the Dijkstra algorithm you apply should really end up having. Think about that one. You will see exactly how you can also appreciate the algorithm itself is approaching to that particular minimum. Okay? Figure out yourself first. And then you want to do the table row by row. Yeah, I think for the assignment, I kind of asked you to do a table. So I'll be flexible, right? It's only for participation. But you want to put in a format that you kind of feel comfortable, that you can easily like extract or derive during the test or the exam. Doesn't need to be like in Word document or Excel. Doesn't need to be polished. No. So even if you draw some sketch on the paper and take a scan, take a photo, convert to PDF, I'm okay with that. No problem. Question?
Well, we have to show all our steps, like the individual, like 0 plus 40 is less than.
Okay, so good question. I would say for at least for the assignment and the practice, I would suggest try 1 or 2 very thorough walkthrough. That can also help you understand about the algorithm itself and also looping variant later. In the actual exam or test, I cannot say for sure I will not, but not very possible I would just ask you to show every iteration. I might say, now give me iteration number 3, or give me iteration 2, something like that, right? But I want to be able to get there and then show that particular row in detail. Okay, so we got about 15 minutes. I want to talk about something conceptual, like called looping variants. So this Dijkstra algorithm here, to understand about how it works, is definitely only one step. But the second step is we want to prove its correctness. To really prove its correctness, we got to understand something about its looping variants, which we'll see maybe more detail on Wednesday. But before that, let's understand what a looping variant is. Okay. I have the simplest example, and also in the context programming for you to kind of conceptualize how it works. But let's see. Okay. Let's now see the slides. Okay, is that something we did? Right, there's another exercise you can try, but this one here, you can use calculator for this one here, that's okay, right? The numbers here are a little bit not pleasant to really manipulate, but that's an example I kind of got from one of the textbook. So this one here, this is already kind of finished for you at the initial setup. You can see BWI in the middle there has got a D value, capital D value 0. Everything else has the plus infinity. So you can try to see how you can calculate the shortest path from BWI. You can also give it a try. Okay, you can print it out and then just try it out. Okay, that will be another exercise you can try. Okay, and let's now talk about very quickly about loop invariance. Okay, just before that, let's now talk about algorithm in general. There'll be some notation. We gotta agree. And when we talk about iterative algorithm, let's say we focus on the while loop. Not for loop. For loop, of course, you can always convert your while loop into for loop as well. Let's say while loop. So we are now in the context of some iterative algorithm. So this is some iterative algorithm. Okay, specifically, this part here is outside the iterations. So this one here is basically initialization. Or you can say preparation for iterations. They are not part of the iteration. For example, you can see for the Dijkstra algorithm, this is what we did, right? Even before the first iteration. That's really initialization. Okay? Okay? So just use some symbol. I say S over here standing for programming statements. So initialization itself can be arbitrarily complicated, but usually it might just be some if conditional or maybe a series of variable assignments, right? So S over here is some programming statements. Programming statements. Right here, okay? And then we got a while loop. And let's now be careful here. So there will be some Boolean condition here called B, right? Star, star. And I'm pretty sure you know this, but let's write it down just to be sure. This Boolean condition here simply means as long as B is true, keep executing the body of the loop. As soon as it becomes false, exit from the loop. Okay, let's write it down. As soon as, okay, let's say there are two ways to interpret this. Both are important. As long as B is true, execute the body of the loop. Okay, you can think about this as the body of the loop, which itself will be several programming statements, right? Another time. That means one more iteration. As soon as B is false, exit from the loop. Okay. So normally, I would like to call this like a stay condition for you to stay in the loop. As soon as the negation of B is true, exit from the loop. Okay, I'll write it down just for your information here. You can think about right here, the B here, we can call B the stay condition to stay in the loop for another iteration. Not the case B, or if you like more logically, negation, right? Not the case B will be the exit condition. Right? So that's about the algorithm itself. And now, there might be some precondition, there might be some postcondition, right? When we talk about abstract data type, we actually talk about precondition, postcondition, right? So think about the Q here is what we call the precondition. Here. And right here will be the postcondition. Precondition is like an assumption we are making. Let's say, for example, wow, we actually talked about this when we gave that little lecture, in the beginning of the semester. If I want to do a binary search on this array, precondition would be? Array sorted. Good. It's okay. Yeah, I just wanted to make sure you're paying attention. Good. So now, what about Dijkstra algorithm? What will be the precondition?
All initialized to infinity.
That one's more like a part of initialization already. That one is already assuming that you already satisfied the precondition.
Non-negative.
Non-negative for what? Weights. Okay, good. Awesome. Okay, we'll do that later. We'll just discuss it verbally. So guys, how about postcondition for the Dijkstra algorithm? Postcondition is like if assuming that the algorithm terminates, what can we say is true? All the vertices are? Is the shortest path, right? That's what you meant to say. Maybe?
Well, yeah, and that too.
Okay, that too. Why don't we write it down, okay? Yeah. Yeah, just more about notation, okay? Think about, I usually put in brackets. And then, let's say here we got Dijkstra algorithm. And then we got R here, right? So this is the part that we already talked about, right? We did most of today actually talking about it. And this one here is about precondition, okay? And as you guys correctly said, the weights of between all the vertices, let's say U and V, should be larger than or equal to 0. And here, U should be a valid vertex, and V should be a valid vertex as well. Okay? So that's really non-negative. And the postcondition over here, okay, basically is something that's actually on the slides. I'll show to you implicitly right here. Okay, let me just go back to that slides and then I'll show you. Right here. These two. The postcondition is basically about the property of the capital D and also the path, basically. All right? There are two postconditions. Number one, the capital D of some vertex V is exactly equal to the, let's say, X and V, where X is the start vertex, the single source that we're talking about, right? Capital D is equal to lower d. And number two, the reverse of ancestor path gives the shortest path. Okay, so you can think about this is more like a complete specification for the Dijkstra algorithm. So just a question before that. So whenever, let's say, if you decide to one day to implement the Dijkstra algorithm, what kind of checks should you really do before and after the execution? Before that, you should really check that all the weights are non-negative. After the algorithm, you got to check to see the one you have for D, and capital D, and also ancestor path are really the ultimate one you can get to for the shortest path. Question?
I was just gonna, what was capital D again?
Anybody would like to help before I have to clarify? It's important. Anybody would like to try?
I assume one of them is like the shortest path and one of them is just the path between the two vertices.
Actually, they are both in some way are the shortest path. They are. But I'll clarify. Guys, give it a try. What's the difference? It could be an exam question. So now, in general, when I talk about Dijkstra algorithm, we got little d here, which takes the source x and some vertex v. I also got a capital D for that vertex v. How should I understand about these two?
The temporary shortest path and the final shortest path.
That's pretty good. So which one's the temporary?
Big D.
Big D, right? Okay, good. Okay, let's now clarify this right away. Okay, very good. But I know these are very important details, right? I'm glad you guys asked to clarify. Okay, let's start with the little d. So this is what we call the true shortest path length between x and v, the true. Eventually, we want to get there, eventually. Okay? The capital D. So this is you can think about the shortest path length known so far, that we know about so far. Okay, so this is important. Let me develop a little bit further. When I say known so far, that means we might still learn more about this shortest path. We may have to update the capital D value as we did, right, in the algorithm. So now the question is, I'm going to put it down. Known so far. Question. When is this D of V finalized? Do we have to wait until the algorithm terminates that late, or it's earlier that we can know this is finalized?
I assume it's when you DQ a vertex.
You remove, I wouldn't say DQ because here we talk about priority queue. So priority queue, there's no DQ, right? But you're conceptually right. Yeah, that's right. As soon as we remove the V from the priority queue, depending on which iteration it might be, and that's finalized. We don't have to wait until the very end.
What does it mean by shortest path length? Because it's just in reference to one vertex. That's the part that
So, okay, I'll get there. Let me write it down first. I know what you mean. The answer will be when V is removed from the queue. So Joshua, I believe what you're asking is, so why is here only one single vertex, but here we got two? That's what you're asking, right? So here you can think about this is more like a conceptually, what's the shortest length between x and v? Okay. In order to find it out, we apply the Dijkstra algorithm. To apply the Dijkstra algorithm, you have to start with certain vertex. Implicitly, since I want to know from x to v, I should really start the Dijkstra algorithm from x. So this capital D value implicitly tells me what's the shortest path so far from x to v, x being the starting point. Okay. Okay, let's now also write it down. Implicitly, so this is talking about the shortest path so far from the start vertex to V. So the x over here is implicit, right? Because when you calculate for the Dijkstra algorithm, everything is relative to the start vertex. In our case, before W. All right. Okay, I only got 1 minute. Okay, why don't we say some? Okay, that's about this example here. I think that's really good. So we can refer to it also on Wednesday. Okay. Okay, that's good. So we got precondition, we got postcondition. So now the question is, how can we be sure that this particular loop eventually given that it satisfies the precondition, it's going to satisfy the postcondition. So to really show that, we actually have to learn about something called looping variance. Okay? That's something I would like to continue maybe from Wednesday. All right, so now we'll stop here. All right, thank you so much. And then I would say before Wednesday, try to revisit this particular example here. Will be most ideal if you can try to do it again. So you're completely prepared for your assignment. And I'll release your assignment number 2 tomorrow, the latest. Thank you so much. See you on Wednesday.